reactions of saturated heterocyclic compounds. Now, at the end of the session, you should be able to describe ring opening nucleophilic reactions of the three-membered ring saturated heterocyclic compounds. You should be able to explain where nucleophilic attack occurs in a basic medium for substituted three-membered ring saturated heterocyclic compound. Lastly, you should be able to provide products when four-membered ring saturated heterocyclic compounds undergo acid catalyzed nucleophilic reactions. So to begin with, we are going to look at the nucleophilic reactions of three-membered saturated heterocyclic compounds. Now, the typical examples we are going to use are going to be the arizidine. We're going to look at ethylene oxide and then of course styrene. Now, what is happening is all these three-membered saturated heterocyclic compounds have some energy strain in them. So there's some kind of angle strain that holds the ring together. However, when the size of the heteroatom increases, then the energy strain decreases. So when there's only carbon and hydrogen, you can see that the energy strain is 25 kilocal per mole, whilst as you increase the size of the atom, heteroatom, you can see that in styrene, the energy strain is far less compared to nitrogen in arizidine, and then of course oxygen in ethylene oxide. So please take note of this, that just like epoxides, arizidine and styrene undergo ring opening reaction in both acidic ones and in basic conditions. I will take it one after the other. So in acidic conditions, what we have to note is the fact that the nucleophilic attack occurs at the more substituted carbon, right? So the incoming nucleophile goes to the more substituted part of the ring. So this is a tertiary carbon. So obviously our incoming nucleophile will prefer this side where the H attaches the S. So the ring opening mechanism is seen. So the bond between sulfur and carbon here breaks to open the ring, where the hydrogen attaches through protonation to the heteroatom, and the nucleophile attaches itself to the tertiary carbon, right? So the same thing applies here. We have the nucleophile CH3O attacking the more substituted carbon atom. The next is to look at the ring opening reactions in four-membered ring, five-membered ring, and six-membered ring heterocyclic aromatic compounds. Now, the four-membered rings are less reactive compared to the three-membered rings, and then the five-membered rings are also less reactive compared to the four-membered rings, and it goes on like that. This is because of the energy strain. So, the energy strain in four-membered ring or three-membered ring is far higher, right? So the energy strain in four-membered ring being lower makes them less reactive compared to the three-membered ring heterocyclic aromatic compounds or heterocyclic compounds. Sorry. So they readily undergo acid catalyzed reaction. That's the four-membered ring. They readily undergo acid catalyzed reactions, ring opening reactions, and then the vigorous conditions are required for non-acid catalyzed ring opening reactions. So please take note of that. So when it's an acid catalyzed reaction, yeah, the ring opening reaction is quite simple and straightforward. However, when the reaction is not occurring in acidic medium, then we need more vigorous conditions for the reaction to proceed. So we have here in an acidic media, we have this product being formed, but in non-acidic media, then we need some vigorous conditions to make the reaction proceed. So please take note of the reaction mechanism, the starting material, and the ending products. So in the 5 and 6 membered ring as well, they undergo the same reaction as their straight chain analogs. So for instance, Lactone undergoes the same reaction, the same ring open reaction in acidic media to produce its corresponding ester. And lactam also in an acidic media undergoes the same ring opening reaction where the ring opens from this side to produce the corresponding amide.